Hello, my name is Haley Neidig, and this is my oral presentation 3 for Geology 105. Long before humans, before even the dinosaurs, Earth was still teeming with life. Until, of course, it wasn't. At the end of the Permian period, which was 299 to 252 million years ago, everything died. Well, not everything, but a pretty significant amount of life was wasted. 90% of marine and 70% of land animals were wiped out by some unknown event, which changed the course of history and allowed for new creatures to become the dominant species. We only really found out about the Permian extinction fairly recently in geological terms, paleontologists noticing a strange pattern in the fossil records. After a certain point in the layers of the Earth, there's evidence of a world of abundant life. Go just a little further up, however, and that life all but vanishes. No one is exactly sure of what caused the Great Dying, but scientists think they have some pretty good ideas. There tends to be a consensus on the three main theories within the scientific community. These main theories are impact events, the effects of Pangea on the environment, and a large magma event with subsequent warming. As our understanding of science has gotten better, the Permian extinction only becomes more alarming. At first, we thought it to be a long, gradual process. However, we know now it happened quite abruptly, possibly in a few very short waves. In the way of geological time, we're talking about the blink of an eye. First, let's talk about impact. 250 odd million years is a long time for rocks and geological evidence to survive, and most hasn't. However, scientists have found the ancient rocks in a few places, such as Hungary, Japan, and China. A scientist named Luann Becker, who is a geologist at the University of California, Santa Barbara, led a NASA-funded team to these sites. She and her team found clear, familiar signs of a major collision, and signs that the asteroid that hit was as big or bigger than our large friend, Mount Everest. Deep inside these rocks, Becker's team found fullerene molecules. Trapped inside were helium and argon gas. At first glance, that isn't that strange. However, the particular isotopes deep inside were unusual. These soccer ball-shaped molecules had a high number of isotopes that were much more common in space than on Earth. This indicates that something, likely of the asteroid or comet variety, must have brought these molecules to Earth. Luann Becker had found similar molecules in rocks associated with two other known impacts, the Cretaceous-Tertiary impact, which was 65 million years old, and the Sudbury impact crater, which was 1.8 billion years old. They also found fullerenes containing these isotopes in some meteorites. All of this together makes a pretty compelling case that an asteroid touched down on Earth during the Permian extinction. A different team, spearheaded by Kunio Kaiho of Tohoku University, found some other isotopes of note. The Permian-Triassic boundary layer is enriched with light sulfur, much like our mantle. This suggests that something spread this sulfur from the mantle all over the surface. An asteroid impact is more than capable of this, and the primary guess. The initial blast from such an impact, especially from a rock the size they assume, would kill a lot of things in quite a large area. It would also create millions of tons of debris, blocking out the sun. Impacts also create large amounts of heat, which would release a ton of greenhouse gases, creating some significant warming. Now, impacts aside, the geography of our Earth was changing pretty drastically. During the Permian, plate tectonics pushed and pulled everything together, which created the supercontinent Pangea and the superocean Panthalassa. Weather patterns and ocean currents shifted, sea levels dropped, and the amount of shallow ocean decreased drastically. This shallow ocean was the home of many species, especially to those who were food for a significant amount of animals. This loss of habitat wrecked the food chain and led to the loss of many organisms. The worst part, though, wasn't the hit to the ecosystem. It was a loss of major currents. Water becomes oxygenated when you move it around, much like when you have a fountain in a pond, and the currents did that for the ocean. However, when you lose those major currents, you lose a significant amount of oxygen. If Panthalassa became anoxic, meaning greatly deficient in oxygen, marine life would be decimated. The death of that many marine animals, on its own, would have significant negative effects on other animals and plants. The Panthalassa superocean seems to have become anoxic in stages, and it recovered in stages, taking 10 million years to finally recover. It took it at least that long for reef dwellers to appear again in Triassic fossil records. Now, back in '96, a man named Hank Fisher found an abundance of fungus fossils within the Permian-Triassic boundary layer. There are hints that this layer, enriched with fungi, is the record of a worldwide crisis, the fungi thriving on and breaking down ridiculous amounts of vegetation that had been destroyed. Such a layer is unique within the record of the past 500 million years, making it very interesting. Mentioned briefly in the impact section, warming of the planet could have changed and killed a lot. During the end of the Permian, our planet was experiencing a large volcanic event. In what is now called Siberia, 1.5 million cubic kilometers of lava poured out from the crust. That's over 1 million times larger than the eruption of Mount St. Helens in 1980, which was only 1 cubic kilometer of lava. And it's not hard to see the destruction that did. An eruption like this would have burned a lot of land, filled the atmosphere with dust and ash, and released a significant amount of harmful, warming greenhouse gases. The ash would have blocked photosynthesis, and the change in climate caused by this warming and by the lack of plants, it could have flipped weather patterns, causing wetlands to dry up and dry lands to flood. Evidence supporting this hypothesis has been found in several places, but especially in recent investigations in the Caledon River in South Africa, according to an article from PBS. The Karoo Basin, which contains the Caledon, has been called the best studied record of vertebrate taxa across the Permian-Triassic boundary. It records a complete stratigraphic record of the systems in the interior of the southern area of Pangaea, as well as containing many vertebrate fossils. The Permian-Triassic boundaries find correlation with marine stratotypes of the same boundaries, which dates the one in the Karoo Basin at 251 million years old. For clarification, a stratum is a layer of rock in the earth. A stratotype is a group of layers of rock designated as defining a named layering unit or boundary. And a stratigraphic record is a record of layers of rock within the earth. The Karoo's fossil record of Permian plants is less complete than its record of vertebrates, but the other areas of Africa record a major vegetative extinction at the boundary. The main cause of environmental change in the area was thought to be a pulse of major tectonic activity, causing the basin to experience uplift. This uplift ranged from 10 to 30 meters. This tectonic activity could have been caused by Pangaea, an eruption event, or even an impact. Altogether, it is highly likely that no one of these ideas was the primary cause. Recent discussions have led to an acknowledgement of the case of a perfect storm. While each of these things would have been absolutely devastating on their own, a mix of warming, Pangaea, and an impact would be needed to create something as quick and drastic as the Permian extinction. As science continues to advance, I hope that we are able to find out more about this mystifying event and to find the causes. Thank you very much.